mass relationships in chemical reaction. I will provide a link for the material in the description of the video. So for any chemical reaction, I have to have a certain amount of the reactant to give me a certain amount of a product. If I looked here at for this example, if I have A plus B to give me C, I have to have a certain amount of A that I can mix with B in a certain conditions to give me C. If I start here by an element, it's easy. So if I have element such as iron, so I can just take the atomic mass of iron that enters the reaction, and if I have 1 mole of A reacting with 1 mole of C to give me 1 mole of if I have 1 mole of A plus 1 mole of B to give me 1 mole of C, this means the amount that I'm entering the reaction is 56 grams. But what if I have a compound? So to start any chemical reaction, I have to know the molecular mass of each part of the reactants. So the sum of atomic masses of individual atoms will give me the molecular mass. So if I have something like H2O molecules, so the sum of the two atoms, or the atomic mass of the 2 hydrogen atoms plus the oxygen atom will give me the molecular mass. So I have 2 oxygen multiplied by my atomic mass is equal to 1 plus my oxygen. I have 1 atom of oxygen by my atomic mass is equal to 16, and the sum of this would be 18. So H2O molecular mass is equal to 16 AMU. For ionic compounds, something like NaCl, if I have 1 atom of sodium and 1 atom of chlorine, so I multiply 1 by the atomic mass of sodium, which is equal to 23, plus I have only 1 atom of chlorine, multiplied by the atomic mass of chlorine, which is equal to 35. This means my molecular mass of sodium chloride would be equal to 58 atomic mass unit. So I can use a spectrometer to detect the molecular mass of any compound. Like we see here, this is an schematic for atomic mass spectrometer, where is lighter ions would be deflected more than the heavier ions, and from my chart I can detect the molecular mass of the compound. Now let's go back and calculate some molecular masses for some compounds. Example 1. Calculate the molecular mass in AMU for the following compounds: sulfur dioxide and caffeine. First, sulfur dioxide. So sulfur dioxide formula is SO2. This means I have 1 atom of sulfur and 2 atoms of oxygen. From the periodic table, I could see that the atomic mass of sulfur is equal to 32. Multiplied, I have only 1 atom, plus I have 2 atoms of oxygen with atomic mass 16 for each one of them, and the sum of that would be equal to 60 for atomic mass unit. Number B, for caffeine. So I have 8 carbon atoms and 10 hydrogen atoms, 4 nitrogen atoms, and 2 oxygen atoms. First, I have to know the atomic mass of each one of them. For carbon is 12, hydrogen is 1, nitrogen is 14, and like we said before, oxygen is 16. So the sum of individual atomic masses would give me the molecular mass. So the molecular mass of caffeine would be equal to 8 multiplied, because I have 8 atoms, multiplied by 12 plus I have 10 atoms of hydrogen, so I multiply 10 multiplied by 1, plus I have 4 atoms of nitrogen multiplied by 14 for each one of them, plus I have 2 oxygens multiplied by 16 atomic mass for each one of them. This would be equal, the sum of that would be equal to 190 for atomic mass unit. Let's look at another example. Methane CH4 is a principal component of natural gas. How many moles of methane are present in 6 grams of methane? So first I need to find out what is the molecular mass of methane. So molecular mass of methane would be equal the number of atoms of carbon, which is 1, multiplied by the atomic mass of carbon, which is equal to 12, plus the number of atoms of hydrogen, which is 4, multiplied by the atomic mass of hydrogen, which is equal to 1. This would be equal to 16 AMU. I have 16 atomic mass unit for the molecular mass of methane. This means I have 16 grams of methane in 1 mole of methane. So if I have 6 grams of methane, how much I will have? How many moles do I have? So to be able to solve that, number of moles would be equal to the given unit, which is 6 grams, multiplied by, if I have 1 mole, which is the desired unit, divided by 16 grams, the molecular mass of methane, would be equal to 0.378 mole of methane. This means each 6 grams of methane contains 0.78 grams moles of methane. This means each 0.378 moles of methane contains 6 grams of methane. Now let's look at another example. How many hydrogen atoms are present in 25.6 grams of urea, which is used as a fertilizer in animals' feed and in manufacture of polymers? The molar mass of urea is equal to 60 grams. First, I have to know that each 1 mole of urea contains 4 moles of hydrogen. So first, I have 1 mole of urea is equivalent to 4 moles of hydrogen, and I also have to know that each mole of hydrogen contains Avogadro's number, which is 6.022 multiplied by 10 to the power 23 atoms. So what I need to do now is convert the grams of urea into moles. Then, after I convert the grams of urea into moles, I need to compare that number of moles to the number of moles of hydrogen to know how many moles that 25.6 grams of urea contains, how many moles of hydrogen. Then those moles of hydrogen are equivalent to how many atoms, if I know that each mole should be equivalent to 6.22 multiplied by 10 to the power 23 atoms, which is Avogadro's number. So the number of atoms, hydrogen atoms, would be equivalent. My given unit, which is the 25.6 grams of urea, would be equal to, multiplied by 1 mole. I know that 1 mole of urea is equivalent to 60 grams of urea. Then I will convert what I'm given here, which should be equivalent to the number of moles of urea. If I know that how many moles of hydrogen, I know that each mole of 4 moles of hydrogen is equivalent to 1 mole of urea. And then I will convert these two atoms by multiplying the Avogadro's number, which I know it is equivalent to 1 mole of hydrogen. Here's our atoms. So if I calculated this one, it will be equal to 1.03 multiplied by 10 to the power 24, and my unit would be in atoms. Now moving to calculate the percent composition of a compound. I use this method to determine the purity of a sample. So if I want to know the percent composition of an element, I multiply by the number of the atoms of my element by the molar mass of the element divided by the molar mass of the compound multiplied by 100 to get the percentage. If I want to know the percent composition of each component, the hydrogen and oxygen, first I need to know the molar mass of hydrogen peroxide, which is equal to number of moles of hydrogen multiplied by the atomic mass of hydrogen, which is equal to 1, plus the number of atoms of oxygen, which is 2, multiplied by the atomic mass of oxygen, which is 16, and that is equal to 34. This means my molar mass, in each 1 mole, I have 34 grams of H2O2. If I want to calculate the percent composition of hydrogen, it would be equal to the number of atoms of hydrogen, which is 2, multiplied by the molar mass of the atomic mass of hydrogen, which is 1, divided by the total molecular mass, which is 34, and I will multiply it by 100 to get the percent, which is equal to 5.926%. And if I need to know the percent composition of oxygen in this compound, it would be equal to the number of atoms of oxygen, which is 2, multiplied by atomic mass of oxygen, which is equal to 16, divided by the molar mass of hydrogen peroxide, and to convert it to percentage, I have to multiply by 100, and this would be equal to 94.06%. I have to know that both of them, the sum of both percentage should be equal to 100, which is my total percentage. Let's take another example. Phosphoric acid, HCbO4, is a colorless acid. Calculate the percent composition by mass of hydrogen, phosphorus, and oxygen in this compound. First, I need to know the molecular mass of phosphoric acid. Phosphoric acid, H3BO4, is equal to, I have 3 hydrogen atoms, so 3 multiplied by 1, the atomic mass of hydrogen is equal to 1, plus number of atoms of phosphorus is equal to 1, multiplied by the atomic mass of phosphorus, which is 30.97 grams, plus the number of atoms of oxygen, which is 4, multiplied by the atomic mass of oxygen, which is 16, and that would be equal to 97.99 grams. So the percent composition of hydrogen would be equal to the number of atoms of hydrogen, which is 3, multiplied by the atomic mass of the hydrogen, which is 1, divided by the molecular mass of phosphoric acid, which is 97.99 grams, multiplied by 100 to convert it into percentage. This would be equal to 3.086%. Now the percent composition of phosphorus would be equal to 30.97, which is the atomic mass of phosphorus multiplied by only one atom divided by the 97.99 grams of the phosphoric acid multiplied by 100 to convert it into percentage, which is equal to 31.61%. The percent composition of oxygen would be equal to number of atoms of oxygen, which is equal 4, multiplied by atomic mass of oxygen, which is 16, divided by the total molecular mass of phosphoric acid, which is 97.99, multiplied by 100 to be able to convert it into percentage, which is equal to 65.31%. Now let's look at this example. Ascorbic acid, vitamin C, is composed of 40.92% carbon, 4.58% hydrogen, and 54.5% oxygen by mass. Determine its empirical formula. So now I'm giving the percentage and I'm asked to give my empirical formula. First, I need to know the number of moles of each component. First, for carbon, I will multiply the 40.92% of carbon by 1 mole of carbon divided by the number of grams in each mole of carbon, which should be equal to 3.407. This means I have 3.407 moles of carbon. For hydrogen, number of moles would be equal to the percent composition of carbon, which is 4.58, multiplied by, if 1 mole contains 1 grams of hydrogen, this means the number of moles would be equal to 4.54 mole. Number of moles of oxygen would be equivalent to percent composition of oxygen, which is 54.5 multiplied by 1 mole of oxygen has 16 grams of oxygen. This means the number of moles is equal to 3.406 mole. So C has 3.407 moles, H has 4.54 moles, and oxygen has 3.406 moles. If I divide 3 of them by 3.406, this means my carbon now, if I cancel this with that, it's approximately is equal to C1, and it should be equal to 1.33, and the oxygen here for 06. So if I divide it here by 306 is equal to 1. I need to multiply by a factor to be able to get a whole number without a fraction. I will try to multiply by 1. If I try to multiply by 1, I will have here 1.33, which is still a fraction. If I multiply it by 2, if I multiply 1.33 by 2, it is equal to 2.66. And if I multiply it by 3, this means it will give me 3.99. If I try to approximate this one, it is almost equal to 4. So the number that I can multiply my formula with is actually the 3. So I multiply all of them by 3. So if I multiply C by 3, it will be C3. And the H from here, it is almostly equal to, approximately equal to 4. And I multiply the oxygen by 3 is equal, oxygen is equal to 3. So this is the empirical formula of ascorbic acid. Now let's look at another example. Chalcopyrite CuFe S2 is a principal mineral of copper. Calculate the number of kilograms of copper in 3.71 multiplied by 10 to the power 3 kilogram of chalcopyrite. First, I need to determine my molecular mass of the chalcopyrite, which would be equivalent to the number of atoms of copper, which is 1, multiplied by 6.63.69 plus the number of atoms of iron, which is 1, multiplied by the atomic mass of iron, which is 55.6, plus the number of atoms of sulfur, which is 2, multiplied by the atomic mass of sulfur, which is equal to 32. That would be equivalent to 183.5 grams. So the percentage composition of copper in chalcopyrite would be equal to 63.69 divided by 183.5 grams of the chalcopyrite multiplied by 100%, which is equal to 34.63%. So the percent composition of copper I needed to convert it to a fraction instead, so which is equal to 0.33463. Now I can if I multiply the fraction of the copper by the weight of the chalcopyrite, I can get the amount or the number of grams of copper in the chalcopyrite. So the mass of copper in chalcopyrite CuFeS2 would be equal to 0.3463 multiplied by the grams of chalcopyrite, which is 3.71 multiplied by 10 to the power 3, and this would be equal in kilograms. This means the mass of copper in the chalcopyrite would be equal 1.28 multiplied by 10 to the power 3 kilograms. I can use the empirical formula to identify compounds. Example for that, if I burn ethanol, I can obtain the mass of hydrogen and the carbon. From that, I can calculate the mass of oxygen. So if I burned 11.5 grams of ethanol in excess of oxygen, I can get 22 grams of carbon dioxide and 13.5 grams of water. To be able to get to know the mass of carbon in the 22 grams of carbon dioxide, I multiply the 22 grams of carbon dioxide by 1 mole of carbon dioxide divided by the 44, the molecular mass of carbon dioxide. Then I know that each mole of carbon dioxide, each mole of carbon exists in 1 mole of carbon dioxide, and that each around 12.1 grams of carbon exist in 1 mole of carbon. From that I get, this means I have 6 grams of carbon. I will also do the same thing for the hydrogen, so the mass of hydrogen would be equivalent to the mass of water, 13.5 grams of water, multiplied, if I know that each mole of water contains 18.02 grams of water, and I know that 2 moles of hydrogen are present in 1 mole of water, multiplied by the grams of present in 1 mole of hydrogen, this would be equal to 1.51 grams hydrogen. So now I know the mass of hydrogen and I know the mass of carbon. If I add to be able to know the mass of oxygen, would be equal to the total mass I used at the beginning of the reaction, which is 11.5, minus the mass of carbon, which is 6, plus the mass of hydrogen, which is 1.51. This means the mass of oxygen would be equal to 4 grams. Now I can know the number of moles of each element present in 11.5 grams of ethanol. Number of moles of carbon would be equal to the grams that I obtained from the previous step, which is the 6 grams carbon. I know that each 1 mole of carbon contains 12 grams, 12.01 grams of carbon. This means I have 0.5 carbon moles of carbon, and moles of hydrogen would be equal to the grams I obtained, 1.51 grams, multiplied. If I know that each mole of hydrogen contains 1 grams of hydrogen, this means the number of moles is equal 1.5 moles hydrogen. And moles of oxygen would be equal to the grams present in the 11.5 multiplied by, if I know that 1 mole there are 16 grams of oxygen in each mole. This means the number of moles would be equal to 0.25 moles oxygen. This means I have 0.5 moles of carbon, and hydrogen I have 1.5, and the oxygen is equal 0.25. If I try to divide the 3 of them by 0.25, this means I have C, which is equal to 2, and H would be equal to 6, and O is equal to 1. And that is the empirical formula of the ethanol. Now we could see that we can, from the percent composition, calculate the empirical formula, and from the empirical formula we can know the actual formula and identify the compound. Example: a sample of compound contains 1.52 grams of nitrogen and 3.47 grams of oxygen. The molar mass of this compound is between 90 grams and 95 grams. Determine the molecular formula and the accurate molar mass of the compound. So first, I can know the number of moles of nitrogen, which is 1.52 grams, multiplied by the 1 mole of nitrogen actually contains 14 grams of nitrogen, and that would be equal to 0.108 mole nitrogen. Now we need to calculate also number of moles of oxygen, so that will be 3.47 grams multiplied by, if 1 mole of oxygen contains 16 grams of nitrogen, this would be equal of oxygen. This means oxygen would be equal 0.217 mole oxygen. From that we could see that the ratio between N and O is equal 0.108 to 0.217. So if I divide this one by 108, and this also by the same number 0.108. This means the N would be 1, and the oxygen, this on the calculator will be approximately to 2. This means my empirical formula is NO2. So now I need to calculate the molar mass of this empirical formula. So molar of empirical formula NO2 is equal to the N, which is equal 14 plus 2 multiplied by 2 oxygen atoms with atomic number 16, and this would be equal to 46 grams. Now if I look here, I have 460 grams of for the empirical formula. So if I divide this empirical formula molar mass over one of the suggested molar mass, which is 90, I will get the ratio between, so the ratio between the molar mass empirical and actual, which is equal to 46 grams divided by the 90 grams, which is equal approximately 2. This means my empirical formula, I have to multiply it. If my empirical formula, I have to multiply it by 2, because if I have the empirical formula NO2, this means multiplied by 2 is my actual formula. So the actual formula would be equal to multiplied by NO2, which means which is equal N2, or I could say NO2. Now let's calculate the molar mass of my actual formula. So the molar mass of my actual formula NO2 by 2 is equal to, I have to multiply this one by the nitrogen and by the oxygen. So 2 by 14, plus 2 by 16, which is equal to 92. I could see that 92 grams. This means my molar mass actually lies between the 90 grams and the 95 grams. On my next video, I'll be talking about limiting reagent and the reaction yield. Thank you and goodbye.